In this exploit demo, I have a vulnerable application called stack vulnerable console C. This application simply reads a file, and it accepts the file name as an argument while starting it, or it asks user to give a file name if no argument is given. So there are programming bugs in this code. The first one is, of course, printing the file name if it is given. So we see that there is a problem here because it is a format string bug, and it simply reflects the name with actually not using any protection and not actually mentioning about this type. Also, it uses string copy, and it actually copies the content to the fname variable with no boundary check. And also it uses a function file read that reads the file content. If we look at the data and the source code, we can see other problems here. The first one is it uses fgets to read only 1255 bytes of this file and puts this in the buff as chars. But also, it again uses string copy, str copy of this buff size to the data pointer given here. And if we check the data is unfortunately not available to handle all of it if it is more than 1000. So multiple programming errors that can be exploited through that way. One of those is actually a format string bug. Another one is stack overflow because of the str copy in different locations. And another one is, of course, file read and str copy for the data. This application also asks the user's input if there's no argument given. That's why the printf, the format string bug, is also available right here in 31st line. So the compile will have warnings about the format string. That's why we need to ignore them using W all. To compile this one, we simply use our makefile. I provided a makefile called makefile.bcc32, which actually compiles the application as expected. So the application is compiled, and now we have stack vulnerable console exe. How it runs is quite simple. If the file name is given 123, it says that file does not exist. If argument is not given, but file name is given here, it says that file does not exist, but still asks the additional file names. Control C can exit the code. So that is our vulnerable application. The vulnerability can be triggered in several different ways. For example, %x, 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 that actually triggers something for us. As you see, it doesn't reflect the %x, it actually leaked some data. And if we pay attention, there is a data here quite valuable to us. Let's look at the code and how it works. In our ASLR exploit, we have other examples in the repository as well. And these examples are designed to explain the way. For example, I simply put 1500 of chars to actually create a stack buffer overflow, and I have seen the alignment, and I calculated everything one by one, and that is in the repository. However, this demonstration is based on the ASLR exploit of it. So simply, we will walk through the ASLR exploit and how we actually exploit this application. Simply, we identify that there's a leak trigger here, which is highly important for us. After 6 of %x, we can see the address is leaking and the address belongs to NTDLL. And after 6 %x, %x, we also see another leakage here, kernel 32 address. So it repeats again and again. So what we can use here is these two addresses as their base address, because our application has some protections disabled, unfortunately, because the compiler does not have ASLR support, rebase support, or safe support. safe support. I'm not abusing those. My rope chain here is based on NTDLL and kernel 32. So I assume that my applications, static features or security features disabled do not affect the exploitation. That's why my exploit is relying on the NTDLL and kernel 32 DLL addresses leaked. To do so, we simply call this process with the leak trigger, and then we set the standard input, output, and error pipes, and output simply gives us the NTDLL and kernel 32 leakage. This leak, the addresses, will be used in our code to calculate the gadget addresses as they were previously fixed in the DEP exploit. In ASLR, they are relative, and they are actually uses the MTDLL and kernel 32 addresses as constants. If stack vulnerable console would have different DLLs or modules to be loaded, and they will be also suffering the same problem, such as no ASLR, no safe or no rebase, then we could actually build our exploit against it. Instead, for this demonstration, an argument's sake, I built a ROP DLL based on these leaks. Let's see how these leaks work. I'm cleaning the screen and calling the ASLR exploit. When we call the ASLR exploit, it simply retrieves the NTDLL leak and kernel 32 DLL leak. And after that, it prepares a console text. And console text is actually our data to push this application to get code execution. Let's see whether or not it works, then walk through how it works. When we use this, it worked. To make sure that ASLR is still there, in our memory, actually in our registry, we can see memory management does not have move images set here. It has been restarted, so it is effective. Also, I used always on for DEP to enable it as well. So our exploit works under ASLR and DEP conditions, but how? And that is the actually demonstration of it. Now we use Immunity Debugger to load our stack vulnerable console.exe with the console text parameter, which is the file we generated. Let's open it and walk through this file. And we can see our content right here. Firstly, I run the application. This is the entry point. And we have a debugger breakpoint set. This debugger breakpoint set to see how it works after, actually right before the corruption starts. The breakpoint is right there, 4012AF. That address is actually our breakpoint address, and it gives us where it fails. Pop, EBP, and ret instructions actually trigger an error here. If EBP doesn't have any valid address, returning point actually gives us the stack overflow. Actually, not overflow, more than that, the application crashes. But we need that overflow to be driven very well to take control of the application and application flow here. That's why we put the debugger here, and let's hit the debugger. As can be seen through this address, our debugger is there. Let's go back what we have as functions. We will go through those functions shortly as well. This one is designed for the stack, because what we see here is the stack doesn't have enough space for us, as it also overrides the set chain. Let's go back in our code and let's collapse these functions to review after that. Let's see how our stack works. We have our payload that has shellcode and also our rope chain, and there's a size here fixed, which is 1032, and exactly we hit after that EBP. So EBP is quite important for us because that triggers the bug for us. And if we keep writing, we influence the EIP, the instruction pointer. And also, if we keep pushing it, we also hit eventually seh record and end seh record, next seh records. So they are quite actually limiting us and our capabilities because we have only limited space to put our shellcode here, which is undesirable because we need more space for our payload to open the memory and work on. So what we need is to leverage actually the padding 1032 to put our payload. And in our breakpoint location, if we go back, we can see there is a lot of space here, and now it starts actually make sense. We have our payload rope chain placed here. That means we need to jump back in time to see how it goes. So we need to jump back to our certain stack location that has the payload. That is the reason of all this exercise. That's why we have two rope chains, not one. The first rope chain is actually designed to jump back. It only has two instructions, but also some stack adjustments and fillers. But two rope gadgets required for this. And when we execute this, let's see how it works. Their location is relative, as I mentioned before. NTDLL leak, which is right here. Let's open calculator and pass this. This is our address of NTDLL. And this is NTDLL relative address to add. Let's add this. And as you see, this is a very similar address for us. It is relative because we know the leak position gives us the base address of the DLL. And as the DLL is same for this version of Windows, if it changes, this rope will fail drastically. So we rely on NTDLL, do not change. This location and DLL itself will be intact from the base address given. So DLL doesn't change. That means our distance to the leak position always remains same. That's why, as you see, 7712 was the base address starting, and now it is 77ED, which is a different address, but we can still hit our gadget pop ECX return. That is the way to actually bypass the ASLR. We have a leak, and we are building our actually shellcode, which is rope chain in this case, using rope gadgets based on this leak. Pop EVP is the first actually hit because we put our breakpoint right before this error. So it is here, and when we move on, it pushes BBBB to EVP, and then return our actual code. As we see, we have the control now, and the control is simply this gadget, pop ECX return. Pop ECX return will read this value, which is the value, a negative value, to be added to ESP. That actually gives us the distance between the current ESP and our payload location I scrolled up a couple of minutes ago. So let's work with that. Pop ECX actually loaded this data to ECX, and then we used another gadget when we returned, add ESP ECX. That means the ECX, the negative value, to be added to ESP. That means actually we are subtracting this value from ESP. It also has pop EBP after that, which is undesirable, but it is there because our gadget is there, and that is our gadget. So we need to align the memory accordingly. As the ESP, from now on after that instruction, jumps back to our payload rope chain that will change the memory permissions, we need to align the data accordingly because return will have a distance, which is 4, and also pop EVP will use some data to push to EBP. In this case, we put this data as a start of our second drop gadget. This second drop gadget is designed to use virtual protect, and virtual protect will be called these registers aligned for the knob as well as all permissions, new permissions, the size of the area, and actually we need also some pointers such as jump PSP, virtual protect, and rock knob, which is another return. I used actually Mona to calculate that rope chain. Mona gave me a good starting point. I used bad charts I have detected before, and I asked Mona to prepare a good rope gadget list for me. Firstly, let's adjust the payload. That means 414141 will be going to EBP. Let's push it. And return 4 is actually also changes our behavior. So we need to compensate it right here because it will be aligned. See, it is actually EBP is changing, and EBP now points here, which is our actually size of the memory location. And then we simply start building our stuff. This one is a negative value using neg-ex. We simply turn this to positive, and then we will make this the EBX value. As EBX is pointing out our size, it is there. I'm explaining this part of the rope gadget for a reason, because this was not calculated by Mona, because Mona failed to calculate EBX. So I found these gadgets to serve my purpose. Simply, I loaded this negative value to EX. I used neg-ex to convert this to a positive value. Meanwhile, I had to also align the compensate the memory for pop EBP and other instructions that I am not interested in. Then I found another instruction moving the content of EX to ECX and also ECX to EBX, but not in this order. As this is not in that order, I needed to use it twice. The first one, moving ECX to EBX, which I'm not interested in, but also moves EX to ECX, which is I'm quite interested in. Then EX value changes that I don't care because my value is in the ECX. And when I call this function second time, the first instruction actually moves my value to EBX. Then rest, I still don't care. However, life is not that easy because of the alignments. I need to push some data to actually ESI to keep it intact, as well as return has a size that needs to be compensated. So I need to put some values here, but I also realize that if I put ESI at this level, that will be great because I don't need Mona's ESI calculation. So simply I found the virtual protect pointer, which is this, and calculated this actually variable distance to the leak. And then I actually put this in the ESP to be loaded in this pop ESP instruction. So these are the fillers to compensate the return size. So this is the custom part of it. And then we have actually an easier one. Mona also calculated the good EDX, but it also failed to calculate it properly. So I adjusted this payload, but I also realized that I can actually push EBP here because in this context, I don't have any other instruction dealing with EBP. So if I set EBP in this gadget list, I can also remove Mona's calculation of EBP as well. I don't need any pop EBP because it is there already. So we simply use pop EX to get this negative value, turn it to 40, which is rewrite X, changing the permissions of the memory to make it writable and executable, then actually adding 61, this instruction. So simply this value turned to 40. And then we simply use push ESP because our EX is there, and push ESP will help us in this case because it's a pointer, but it won't run now. It will run when we call virtual protect. That's why it's a pointer going to the EBP that will be used later. Let's quickly review again our alignment. We set the ESI, we set EBP, we set size, we set actually EDX. So we have only easier ones left. So go back to Mona because Mona's payload was so easy because it found pop ECX that gives us ECX. Pop 80 will turn to ROP knob. Pop EX will give us the knob values. And also, Mona's suggestion of push AD was not great. I found this push AD works very well with our current payload, and return is not causing any trouble. That is our ROP chain. When this ROP chain runs, we see how it works. Now let's start with pop EX and see. Pop EX is set. EX is negative now, 425, and pop EBP is there. And our long instruction set is here moving. ECX is hoping, and yes, ECX is now going to EBX, and also we are using pop ESI to get the virtual protect and return 10, and that's why we needed compensation here. And as it is compensated, we have another negative value to add to EX, and then EX will have 61 top of it, then it will be positive for 40, which will be our permission, and EBP is also loaded here. So we have EDX going to EX, which is helping us the rest. Pop ECX, pop EDI, pop EX, and now push AD. So we actually, until this point, solve everything. So push AD gives us almost all these alignments in memory. And alignment is already here to make it sense. It can be compared. From now on, we can see that it will go and return. Return will show us this location, this ESP alignment. That is exactly the virtual protect process, actually page, execute, read, write permission, base address that we hope our payload to point, and everything is set. If we walk through and jump, and then everything is going. So I will leave it as running as is, and then we have the code executed. So this is the demonstration of the ASLR exploit. So we can stand alone without debugger. Let's run this again. As seen, it works. It relies on a couple of things. First things first, it relies on Windows 7 Service Pack 1 Professional and 64-bit architecture. It relies on the binary compiled, which can be compiled using the makefile I pointed out, makefile BCC32. It needs Embarcado born C++ compiler. So you have this test environment. To achieve ASLR, you need to start with the alignments. And as mentioned, instead of using padding with 1032, you will start with 1500s, then use mono pattern create, then find MSB, find the size of everything. When you see that you can take control on EIP, which is right here, and we can actually put our ROP chain to take the control in the EIP, then we have the control. ESP is right after this EIP, right? So if we don't use any EIP because of the location, ESP will be the rest. So EIP will be our point taking the control, and our stack ROP chain will be there. And I put simple debugger points there right after our stack pivoting, go back, say a back jump, because in case of I fail, I'd like to see how and why, but those breakpoints won't work. Of course, when we go back, padding variable will work. Padding variable has firstly payload, which is create ROP chain, which is also virtual protect to change the memory permissions, then shellcode, which is our actually simple Windows 32 shellcode. This can be generated using Metasploit, and the payload has bad chars, and that's why bad chars must be avoided using an encoder, which is Shkataganai in this case. And the payload is 32-bit. I put some knobs here to make it slightly smooth to run, to take the control. But knobs may not be necessary if your memory alignment is good. It really depends on what protections you are dealing with. And we write the output to a file and expect output text to work. As we demonstrated, it works. So this is the end of our demonstration. Simply, you can find the DEP, EIP, and calculations as separate files in the same repository. I hope you enjoyed the demo. Thank you.